Hi everyone, thanks for checking out this video. Okay, so we're getting close here. We're getting close to finally being able to put together our full neural network, and there's really only one thing left that we have to do. So only one thing left, and then we're basically going to be done, and it's going to be time to actually like test this thing out. But unfortunately, this one last thing that we have to do is actually a little bit hard. It might be it probably is the hardest thing that we're going to do with the tensor class so far. Yeah, it is a little bit hard, so I might actually I might take two videos to cover it. I might split it up into this video and the next video, depending on how we're doing with time. But yeah, it is a little bit hard, and you guys are going to see what I mean. But yeah, this is like the last final like obstacle we have to get over until we're finally going to be done. So just hang in there. We're close, but there's one more difficult thing we have to do. Okay. And the reason it's hard, well, one of the reasons is that we're going to be combining two different things, actually. So we're going to be combining an activation function and a loss function all into one operation. And you guys are going to see why we're doing that. It's actually... The reason is because combining them is going to make it easier to calculate the gradients. It's gonna avoid some unnecessary complications of doing them separately and just make the actual math a little bit easier. So that's one of the difficulties, is that we're going to be combining those two different things into one. And then the other difficulty is that I don't exactly know how to say this, but I'm not completely happy with the way I've implemented this last part. I would have liked to, and you guys are going to see what I mean, but it's a little bit like hacky right now. I kind of like hacked it together a bit, in a way that in some ways is inconsistent with how the rest of this code has been so far. You guys will see what I mean, but yeah, I'm not 100% happy with the way I've implemented it. It works. I mean, it does what it's supposed to do, but I'm not completely happy with the actual like organization of the code. And I think it's a little bit sloppy right now. So I'm showing you guys what I have now, but in the future I might try to like improve this part of the SimpleGrad package to try to make it a little bit nicer. You guys will see what I mean. That probably sounds confusing right now, but when we get to it, you'll see what I'm talking about basically. Yeah. Anyway, I guess we'll get into it pretty soon. Just one more thing. I wanted to, for this video, give credit to where I learned how to do this. I learned how to do this from this textbook, Neural Nets from Scratch in Python. This is the textbook of this guy, Saint-Antoine on YouTube. He's a YouTube, like video tutorial creator, really good Python videos, and he has this textbook about how to make neural nets from scratch in Python. And I actually bought the textbook. I treated myself and got the actual like legit hardcover version of it. So yeah, I actually have this textbook. I bought it from his website, and it was pretty awesome. I learned how to, yeah, this textbook and Andre Karpathy's YouTube series were basically where I learned how to do all this stuff that I'm now teaching to you guys in Julia. So yeah, credit to this textbook specifically for teaching me this trick of combining the softmax activation and cross-entropy loss to make the math easier. That specific trick was something I learned from this textbook. So yeah, I recommend that to you guys to check out. Yeah. Okay, that's enough rambling. Sorry guys for the ramble, but now let's actually get into it. So like usual, we have our code so far at the top, so just make sure you run that. And then since we're going to be doing something a bit complicated in this video, and really I'm probably going to make this two videos because it's going to be a little bit complicated and long for this last like final hurdle. Since it's a bit complicated, I'm actually going to, for the first time, start like putting together a simple like test neural network just so we can see what we're dealing with and what we're talking about. So I'm going to start making up like a simple example just so we can get an idea of like what's going on here. Okay, so I'm just going to be a little bit lazy and copy and paste some code here. Okay, so we'll start with a matrix of inputs of dimensions 2 rows and 3 columns. So I'll just print this out to show you guys what it looks like. Just called it inputs. Whoops. Yeah, so this is a tensor. It actually doesn't print that nice. I might try to actually fix this in the code later to make the printing a little bit nicer, but this here before the semicolon is the first row, and then this is the second row. So it does in fact have 2 rows and 3 columns, although the printing doesn't exactly show that perfectly. But yeah, it's 2 rows, 3 columns. So we're calling for this example, we can consider this as if this is like the input like data set, and we're going to say that we have 2 batches. Or sorry, I guess I screwed up the wording here. It's really I should say 2 samples. So this whole thing is a batch with 2 samples and 3 input features per sample. Sorry, I mixed up the wording there. But yeah, each row represents a sample of data that we have, and then each sample has 3 input features. Okay, so then the next thing we're going to do is define, again, just going to copy and paste, being a little bit lazy. We're going to define the weights matrix for our first layer. And so this is going to have 3 rows and 4 columns. So that basically means that it takes in 3 inputs, which are 3 features here, and it has 4 neurons. And then the output, when we multiply the inputs by the weights, is going to be a matrix with 2 rows and 4 columns, because it'll still be our two samples in the batch, and then it'll get input into 4 neurons basically. Okay, and then we're also going to have our biases for the first layer. So this is just going to be yeah, like a row vector tensor. And remember, we can define it. This is still going to be technically 2-dimensional, but we can print out the size of it if we want to, and it should hopefully be, yeah, a row vector, because remember we made it so that we can initialize row vectors just like this. And yeah, then we're gonna add this on for all 4 of the neurons. These are the biases for each neuron in the first layer, and we can add that directly to the product of inputs and weights, because remember we have this like broadcasting capability. So I'll just say yeah, like first layer, and then okay, so now second layer. Yeah, we're gonna have another weights matrix. This one is gonna take in 4 inputs from our 4 neurons in the first layer, and it's gonna have 5 neurons in the second layer. Yeah, and then we're also gonna have our biases for the second layer. Yeah, so hopefully that's making sense to you guys so far. And then so when we do our full thing, it's going to be like layer 1 output. Let's just call it out. It's going to be inputs times the weights for the first layer plus the biases. And then all of that, we're going to do the ReLU activation function for all of those neurons for the first layer. So now we could just print this out and see what we have if we want to. Print layer 1 out. Oh, whoops. Bias is 1. And we can print out the size of this if we want to. And yeah, still our 2 samples in the batch. And then remember our first layer had 4 neurons. So yeah, now we have 4 columns here for each of the neurons. So that's our first layer, and then we can say layer 2 out equals layer 1 out times weights 2 plus biases 2. Yeah, and then we can print our layer 2 out. And yeah, we still have our 2 samples in the batch, and then our 5 neurons in that second layer. Okay, now it's time to talk about what we need to do in this video and probably also the next video because it's going to be kind of long, splitting up into 2 videos. But yeah, so now what we need to do is 2 more things to finally actually have our neural network output for like the full pass through the neural network, basically. So what we need to do is, first of all, we need to do the Softmax activation function for this like final output of this second layer. We're just going to call this our last layer, and because this is something you typically do you do this Softmax activation on your last layer of output to get your output from its raw form into like being like probabilities, basically. So yeah, we need to do that, and then the last thing is going to be cross-entropy loss, comparing final output to one-hot encoded true labels. So basically, we're gonna have like some kind of matrix like this, where for each of our samples, remember we had 2 samples in this example. For each one, we're gonna have some possibility of like which answer in that last layer was the correct answer, and that's going to be encoded with a 1. So if you guys remember, like we had 5 neurons in that last layer, and basically each of those neurons in the final layer represents like a possible class that we're trying to like classify the sample with. And then we encode with a 1 the actual true class of that sample, and a 0 all the ones that were not the true class. And then when we have this like Y true matrix, the idea is to compare this Y true matrix with our true class labels to the final output after doing the softmax activation for this last layer, basically. Okay. So that's what we're gonna try to do. I'm gonna comment some of the stuff out for now, but then we're gonna get back to it. So let's start with this softmax activation. And okay, in this video, it's complicated enough that I think it's gonna be easier before we start actually putting it in the function. I think it's gonna be easier to show you guys this like step by step actually. So you know what? Like first things first, I'll just show you guys what like the softmax activation even is. Yeah, softmax activation function. So it's something like this basically, which I know looks like a complicated formula, but it's basically just like it's like taking all of our values for each of the neurons. Those are these like zi, where we have like one of these z values for each neuron we have, and then we're putting e to all of these, and then dividing by the sum of e to all of them, basically, to get it into like a probability, basically. So I think it'll be easier if I just maybe show you guys the code. Yeah, so this is what it's going to basically look like. So we're going to say like first just exp values equals exp dot layer 2 out. So this is just taking every number in this layer 2 output matrix and just putting e to all of those things. That's what this exp means. And remember the dot means we're doing an element-wise operation here on every element of this matrix. So yeah, maybe I'll just print out and show you guys what I'm talking about here. Yeah, so this is e to all of these things, basically. So maybe I'll just print out both even just to make it even more simple. And yeah, it's going to be different things each time because it's choosing like random numbers to make these things. So yeah, don't worry about if you guys are seeing different numbers, don't worry because these are like randomly picked numbers. Maybe I should have actually set a random seed to, you know what, it's fine, whatever. But yeah, if you guys are seeing different numbers, don't worry because they're just random numbers here. But yeah, so like this here is e to the this, basically, right? So e to the 6.27 blah 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 blah, is 531, like blah blah blah. Yes, we're just putting e to all of those numbers basically. And then once we have e to the everything, then we're going to convert everything into probabilities by basically saying probs equals exp values. Remember, that's this e to the everything. Element-wise division by sum exp values dims equals 2. So maybe first I'll just show you guys what this sum is doing here. Yeah, this is just the row-wise sum. Because remember, we have to all these operations, we have to do them like independently for each sample in the batch, and each row is a different sample. So for each row, we need to calculate the sum for that row, and so that way we can get the probabilities for every element in that row by taking like the e to the whatever it was divided by the sum of the e to all the elements for that row basically. So yeah, this whole thing, this combination is like a row-wise row-wise conversion into probabilities with this softmax activation function. So yeah, now we can also print out the probabilities if we want to. Whoops, sorry. Yeah, so now they're all between 0 and 1, so they make sense to think of them as like probabilities basically. And yeah, so basically this output is basically giving us like a probability, like a predicted guess for each one of these things. And if the classifier is performing well, it should correspond that like the highest probabilities are where the true class is labeled here with a 1. And these ones where it's a 0 should have like low probabilities. Of course, we just did this all randomly, so it doesn't look like that right now. But the idea is that after we train a neural network, we should get to something like that, where like it has a high probability in whichever element corresponds to the true class label. There's one more trick I want to show you guys. So with this code here, this is correct the way it is, but there's something we can do to take like a precaution to just play it safe and make it a bit safer for us. And that's that we want to avoid having a problem where like E is being put to too high of a number. So you can imagine in this layer 2 out, none of the numbers were like super high, but in like a real neural network, if we had like very, very high numbers there, we could start getting like floating point calculation errors trying to put e to them. If it's like e to the million or something, that'll just screw up the computer. You know what I mean? So we're going to do a little trick here, and that's that we're going to say before putting e to everything, we're going to subtract every element in this layer 2 out by the maximum the maximum in that row basically. Yes, we're going to say maximum layer 2 out dims 2. Oh, you know what? Actually, I want to be making these. It's letting me get away with it, even though layer 2 out is a tensor and we haven't defined this exp for tensors. It's letting me get away with it. I think by casting everything to just like a float 64 array. Actually, let me see what type probs is here. Yeah, so it's okay. Sorry, guys. I don't want to confuse you guys further with this, but it's letting me get away with doing this operation on a tensor, even though we haven't defined this for tensors, by just like down casting everything to just a matrix of floats. But yeah, really like the type of this layer 2.out is a tensor. So really, we want to be saying, just to avoid this type confusion, and this is my fault, sorry guys, we want to be saying dot data here. just to avoid having this like automatic typing down to a matrix that it's doing. Yeah, let's avoid that and just say dot data here. And we'll say dot data here too, because remember this is a tensor actually. And yes, it's letting us get away with it, but actually I want to avoid that like type confusion there. So let's just say dot data, just so we're dealing directly with the two-dimensional array. Just make sure that still works. And yeah, so what this is doing, this is resetting all of the values in our layer 2 out array just by subtracting the maximum of the row from them. And then a cool mathematical property is that when we do this subtraction of the maximum from each row like this to make it safe in terms of avoiding like putting e to a very high number, it's actually going to like not affect our final output. So we can actually check and see like what happens when we do that. So we can say like yeah, do it that way, subtracting the maximum, and then do it again where we don't subtract the maximum. So we just call that like x values 2 and then like probs 2. We can get rid of this subtraction here, and then we can print probs and then print line probs 2. And yeah, see, this is just a cool like mathematical property of this type of calculation is that, yeah, when we subtract by the maximum of each row, it doesn't actually change our final probabilities. So we can basically, by doing this, we basically make our calculation safer, just avoiding having E be put to like an extremely high number and get some kind of huge number that like breaks the computer or something. This just makes the code like more safe in terms of avoiding that kind of error, and it doesn't actually change the probabilities we're getting. So yeah, that's a cool thing about it. Okay, so that's our softmax activation function. I'm gonna clean this up a little bit now. One more thing to do just to make things safe on us in terms of just like the numerical calculations and stuff. We're gonna clip the probabilities to make sure we don't get any zeros or ones. We want all the probabilities to like strictly be between 0 and 1. We don't want any zeros or ones because that'll screw up some of our calculations when we have to like take the log of like a 0 or something. So we're gonna say probs equals, or sorry, maybe just to make it clear, I'll say probs clipped equals clamp dot probs 1e to the -7, just defining like a very low number, and then 1 minus 1e to the -7. So yeah, that's just making it so that if any probability is like lower than 1e to the -7, it'll just get set to 1e to the -7. And if it's higher than 1 minus 1e to the -7, it'll just get set to 1 minus 1e to the -7. Just basically making sure we don't have any like too low or too high probabilities, too close to 0 or 1 to the point that it like screws up our calculations. Okay, so that takes care of the softmax activation. And again, we're gonna put this all in a function in a little bit, but I'm just showing you guys just like this first, just to make it easy. So now cross entropy loss. Yeah, so basically we want to have a way to compute a loss function measuring like how far off our probabilities are from this like y true matrix. So like I said, if we have a classifier that's performing well, we would want to have like a pretty high probability in the elements that are labeled with a 1, meaning like that's the element index of the actual true class, and we want to have pretty low probabilities where it's labeled with a 0. And the idea is to like train the neural network to get it to be like that. But in order to do the training, we need a loss function to basically measure how wrong our model is compared to the correct answer. So that way we can update the parameters to try to get it to be less wrong. Yeah. So now we're gonna write the code for that loss function. And yeah, this is called cross-entropy loss. Cross-entropy loss. Okay, so looks like a little bit of a confusing formula here, I've realized, but it's actually not that difficult to calculate. And when we talk about what these things mean, it's actually not very difficult. So this P of X here is just the true probability, like of the actual underlying distribution. And for us, this true probability is either going to be a 0 or a 1, depending on whether that element was labeled as being the correct class or not. 1 means correct class and 0 means it's not the correct class. So yeah, these are just zeros or ones. It's a 1 for the true class label, and then 0 for when it's not the true class label. And then this Q of X here is our model's predicted probability for that index. And some of you guys might notice here is for the ones that are 0, we like 0 in the true, 0 in like the true answer. We can just ignore those because it's going to be 0 times whatever our like model prediction was. And when it's 1, we can actually just basically this whole thing resolves to just like checking each of the indices of the true correct answers, and then seeing what probability we predicted for that true answer, and then like summing those up, taking the log of the true probabilities and then summing those up and then making it negative. Yeah, so it's not so complicated. You might need to like wrap your head around it a little bit, but basically like the higher our, basically we want our predicted probabilities for the true answers to be as close to 1 as possible. So if our model is perfect and all of our predicted probabilities for the true classes were 1, then the log of 1 would turn out to be 0 for all these. We'd be adding up a bunch of zeros. So it'd be 0 times 1, which is 0. Adding it up, we get 0, and then negative 0 is 0. So we'd have 0 loss if we correctly had a probability of 1 for each of the true answers. And on the other hand, if our probabilities for the true answers were very low, then these logs of very low numbers would be very large negative numbers. So very, very like high absolute value negative numbers. So we'd be adding up a bunch of like large negative numbers, and then after we add them up, we'd be making the whole thing negative. So a negative of a negative is then a positive. So we'd have a high positive loss in that scenario, basically. But yeah, if any of that's confusing, maybe it'll be easier when we actually write the code for it now. So basically what we want to do first is we want to just sum up all of the we want to sum up all of the probabilities for the true classes like for every sample in our batch, basically. So the way we're going to do that is we're going to say so probs clipped. Remember, that's our final output probabilities for our model. Dot times, remember, element-wise multiplication here, and then y true. So let's just see what that gets us first. And remember, you guys might have different numbers than me because they're being randomly generated. Let's just see what that gets us. So yeah, that just becomes a 0 for all of our not correct answers, because remember, we can just ignore those. And for all the ones where we have a 1 where it is the correct answer, we get 1 times whatever our predicted probability was for that answer. So yeah, we have our probability of the correct answer for our first sample here, and then probability of the correct answer for our second sample here. Next, we want to just condense these so that we just get, rather than having like a whole matrix here with a bunch of zeros in it, we want to just get like a column vector where we just have these two numbers. So the way we're going to do that is we're going to say, for one thing, we're going to make this a sum, and then we're going to sum on dimensions equals 2, and then call this correct confidences. And then, so now we can print out correct confidences. And yeah, now we have like a column vector here where it just has all of our probabilities that our model came up with for each of the correct answers for each sample. And then once we have that, the next thing to do is get the sample losses. So now we're up to the point where we want to actually we want to actually take the log of each of these. And yeah, we're going to use natural log for now, but really you could use any kind of log. It should work no matter what. But yeah, we'll use the natural log. So I'm going to say sample losses equals negative log dot parentheses correct confidences and parentheses. Then we can print out those sample losses. So that's our loss for each sample, basically. Yeah, so remember we're dealing with a batch here, and we have two samples in this simple case. So we just got the loss for each one of those samples. But in order to have like a final output for this loss function, we want to take the mean loss across the samples. So the way we're going to do that is with out equals brackets sum sample losses divided by length sample losses, and then this should give us like a final single number measurement of our loss for that batch. So this is the average of these losses across the samples, basically. Okay, so this is already starting to be a pretty long video, but there's one more thing I want to do for this video before we start waiting until the next video to do other stuff. So yeah, the last thing I want to do is just put all this, like, or at least start putting it in an actual function. So I've just been showing you guys here like this. Yeah, now let's try to actually start putting this in a function. Okay. So I'm gonna be a little bit lazy and just copy and paste here. Just because it's kind of a long one for this one. Function heading. Okay, so we have a function called Softmax Crossentropy. It takes two input arguments. There's A, which is a tensor, and that's the tensor which is going to be like the raw output of our last layer, basically. So that's like the layer 2 out here. That's what's going to be A being passed into this function. And then it also takes this Y true matrix, which is actually not a tensor. So this is either a two-dimensional int array or a two-dimensional float 64 array. And do you guys remember how in the beginning of this video I was saying I'm like not completely happy with my own implementation of this code so far? Well, this is one of the things I'm not that happy with, is that I would like to eventually get this to be able to handle Y true being a tensor, because everything else is tensors, and it would be nice to be able to handle like Y true also being a tensor. But yeah, for now I just found it easier to just keep Y true like a regular array just for now, just because for one thing we don't need to track the gradients of Y true. Yeah, but in the future I might try to make this more robust so that Y true could also like work if it's a tensor. And then we're also going to have in our forward pass function an optional parameter called grad, which is going to be a Boolean parameter set to true by default. And basically, the reason we have this is because for this function, and this is another thing I'm not super happy about the way I have it implemented right now, but for this function, it's going to be easier actually to calculate the gradients on the forward pass, at least the way I have things set up now. The gradients for this operation will be calculated actually during the forward pass, and then the backward pass is actually going to do nothing. So yeah, I'm not super happy with that because it's like inconsistent with the way we've been doing things. But yeah, rather than the gradients of like a.grad being updated when we call some like final backward function, we're actually going to update a.grad during the forward pass unless this is set to false. Which, yeah, I'm not super happy about that because it's inconsistent with the way we've been doing things. But yeah, that's the way it's going to be for now, and that's what we're going to do in the next video, actually. But yeah, for now we can start filling in a couple of these things, and we're gonna leave some things to the next video too. So yeah, first thing, I'm gonna be a little bit lazy and copy and paste some stuff here because we basically already did it. But yeah, Softmax activation. This is just the same thing we did up here, except I've changed the name of this this tensor from layer 2 out to A, because A is the input tensor here. But other than that, yeah, same thing there. And then yeah, then we'll say like probs. Again, same thing as we just did. Okay, probs clipped. Leave a comment there, deals with zeros and ones or anything too close to 0 or 1. Yeah, I'm just going through this fast because we already did all this stuff. Correct confidences. Yeah, basically just returns an array with probabilities of the correct answer for each. Whoops, I keep saying batch. It's really, because the whole thing is a batch. Each row is a sample within the batch. But yeah, I keep saying the wrong thing for some reason. Okay. And then we have our loss calculation here. Yeah, sample losses, and then the mean of the sample losses. And then we want to eventually return a tensor. So for this, we're gonna yeah, like this line here is basically reshaping out to rather than being of shape 1 comma nothing, it's going to be 1 comma 1, so that we have out is a single number at this point, but we want it to technically still be a 2D a tensor, like holding a 2D array basically. So yeah, out we want to be like, we want this to be the tensor.data for our final output tensor. So we want this to be technically a two-dimensional tensor, even though it only has 1 row and 1 column and it's only holding a single number. We want it to technically be a two-dimensional array that will be like the data field of our output tensor. Okay, maybe I'll copy and paste the comment for that too. And then yeah, result is gonna be like make it tensor out of all this, tensor with just a placeholder for the grad, basically, which is going to do nothing because, well, you'll see in the next video. And then operation softmax crossentropy, yeah. And then lastly, just return result. But we're going to do something in here, and this will be, I'll save this for the next video, but we're going to do something in here where we're going to say like if grad, if this Boolean grad is true, we're gonna calculate and update a.grad in here in the forward pass rather than doing it separately in a backward pass. So yeah, this will be for the next video basically. I think that's enough for this video. Yeah, there's already been a pretty long video, but yeah. Thanks for hanging in there, guys. I know it's taken a long time to finally get to the end of this, but yeah, we're really getting close now. Yeah, I'm proud of you guys if you made it this far. We're really getting close to actually wrapping up this project and putting all this together into like solving a final neural network example project, basically. I think we got one more video to finish out this softmax cross-entropy, and then after that, I think we'll be ready to actually use this neural network to test out with an example. Okay, guys, so thanks for watching, and see you next time.